Hello viewers, so welcome to the third lecture of the course Metal Cutting and Machine Tools. Today we will be discussing more about the geometry of single point turning tools. As you have learnt in the previous lectures, a single point turning tool may be referred to in the tool in hand system, and there we can identify the different planes, the edges which are invariant with the orientation of the tool. After that, we learnt about the machine reference system, in which the tool is placed in a Cartesian coordinate system, where the basic planes correspond to the machine longitudinal plane, the machine transverse plane and the reference plane. The reference plane is the most important, because it is the it is perpendicular to the velocity vector, and it is basically with respect to this that most of the other planes will be defined. So, we have assumed that the reference plane is corresponding, I mean it is aligned in exactly as the orientation of the xy plane, which means that we have assumed that the velocity vector in our calculations is corresponding to, I mean is aligned in the z axis. Okay. So, with this introduction, we have already covered machine reference system and the orthogonal reference system. In the orthogonal reference system, we had the three planes as the cutting plane, the reference plane and the orthogonal plane. The cutting plane contained the cutting edge, and it was also containing the velocity vector. The reference plane was perpendicular to the velocity vector as before, and the orthogonal plane was perpendicular to the cutting plane and perpendicular to the reference plane. After this, we came across the definitions of rake angles and clearance angles defined between two planes placed in a particular sectional plane. For example, orthogonal plane would be orthogonal rake angle was defined to be the angle between the reference plane and the rake surface considered in the orthogonal plane. So, this way I do not want to repeat all those definitions that we have come across. This way we have defined rake angles, clearance angles, cutting angles, okay. And that way we are in a position now to express the relationships existing between different angles in different systems. For example, we might be having a particular nomenclature given in the American system of reference, and we would like to get the corresponding angles in the orthogonal system. So, conversion formulae, they are available, and we will be now having a look how they are obtained. So, let us start. Previous to that, I would just touch yet another reference system, which is called normal rake reference system. As you can see here, okay, as you can see, there is another plane defined as this basic plane is the reference plane. There is another plane defined as the normal plane. Ordinarily, what is this one plane that we are having here? This is the orthogonal plane. First of all, if we start with the cutting edge, this is our cutting edge. The plane containing the cutting edge and containing also the velocity vector here, this is the cutting plane. Perpendicular to the cutting plane and perpendicular to the reference plane, we have the orthogonal plane. but instead of being perpendicular to the cutting plane, if we have a plane perpendicular to the cutting edge, okay, it will be inclined from the orthogonal plane by the angle lambda or inclination angle. Okay. So, it is as if we are simply taking hold of the orthogonal plane and rotating it through lambda, so that it becomes perpendicular to the cutting edge. Okay. Perpendicular to the cutting edge, there is a plane which is called this normal plane. Okay. This normal plane, as you can see, it is making an angle of lambda with the orthogonal plane. It is an inclined plane, it is not vertical, that in that sense. So, with respect to this plane, we can define rake angle, and that is called the normal rake angle, and that in that system we have lambda and gamma n defining the rake surface orientation. So, it would look somewhat like this. We have this tool in the plan view, we have the section in the orthogonal plane, we have the section we have the view in the cutting plane, and then if we make a section this way, I have not shown the section arrows. If we make a section along this particular line, then we will get a sectional view in which normal rake will be coming out here. Okay. So, we would be learning about this system also during our calculations in the later lectures. Okay. So, I will quickly go through the additional angles that we are defining here in addition to the American system, and we have already defined most of them, like orthogonal rake, inclination angle, orthogonal clearance, auxiliary orthogonal clearance, which is on the other flank, etc. And we will be making use of them as we go for the angle conversions. This is the first exercise that we have in angle conversion. For example, suppose I am interested to know what is the relation between orthogonal rake, which is coming out here in this particular, suppose I am interested to know what is the relation between orthogonal rake here and the two rake angles in the American system, gamma x and gamma y. So, I start from here, from this relation. What does this relation state? It states that from this point, if we move down the rake surface in the orthogonal direction, we will reach a point. Say if the orthogonal rake is positive, we go down. So, when from the reference plane the rake surface is going down, okay, as we move away from the nose, as we go down, if the orthogonal rake if the inclination of the rake surface in the orthogonal plane indicates that it is going down, this is positive rake. Okay. So, if we are going down, say a hillside which is inclined, if we are going down this way, down the hillside to a particular point here, where this is a plane surface, but it is inclined, this distance that we go down vertically will be exactly equal to the two segments, vertical segments that we go down if we take yet another path. It simply means that whichever way you are going down, the vertical distance you are covering, if your final position and initial position are the same on a plane, they will be the same. So, the distance I am going down this way, it is equal to the distance, sum of the distances I am going down this way and that way. That is very good, but what is the distance I am going down along the orthogonal plane? Along the orthogonal plane, we will argue that if we reproduce this distance here, in that case we have a tangential relationship. Let us quickly have a look at this. A tool in any section, if I am going down by this distance vertically, say I name this E, if this angle is given, say gamma E, okay. Sorry, this distance is not given, E is this and say B is this much. B is this much, gamma A is this. Therefore, in this case I can write tan gamma E is equal to simply E by B, perpendicular by base. This means that I can express A as B tan gamma E. This is the relation that we will be using extensively in our calculations. So, what we mean to say is this: if on a particular identified section I have a rake angle as shown as gamma A, if this is the distance obtained in the plan view from the top, okay, that distance multiplied by this tangent will give me the vertical distance I am going down. This we will use extensively. So, let us now go back to our discussion here. For example, suppose as I have said, distance I am going down in this direction, orthogonal plane, is equal to the addition of the two distances, vertical distances I am going down in the what do you call it, machine transverse plane, sorry, machine longitudinal plane and machine transverse plane. So, O is equal to S, sorry, the vertical distance down along O will simply be, as we discussed, is equal to O tan gamma 0, sorry, tan gamma O. Tan gamma O is identified here, and therefore, the vertical distance I am going down here is equal to O into tan gamma O, as we discussed. That is the vertical distance down. So, here we have that particular vertical distance, O tan gamma O. This must be equal to these two distances. So, once again we will have S tan gamma x. Tan gamma x is this angle in this plane. This plane is the pi x plane. S tan gamma x plus B, these two segments are equal to S and B respectively. O, S, B are the lengths of these segments, and naturally on this side B tan gamma y. So, B tan gamma y plus S tan gamma x must be equal to O tan gamma O. That is it. We need no other things in order to establish this basic relationship. However, we do not know S, we do not know B, we do not know O, but what we know is, we know that this angle is called phi. If this angle is called phi, the principal cutting edge angle or the plan approach angle, we can definitely say as this is a right angle between these two sides, okay, angle between these two sides must be equal to 90 degree minus phi. So, this one angle must be equal to phi, this must be equal to phi, and immediately if we divide this whole expression, I mean whole equation by O, we have S by O here, S by O. What is S by O? If we take this angle, S by O is nothing but sin phi. So, instead of this one we write sin phi. By the way, I have expressed this, I am sorry, I have expressed this in terms of phi 1, Please understand that phi 1 is equal to 90 minus phi. Okay. I will do one thing. I will let me see if I can write here, then that will be an advantage. So, we can write here sin S by O is nothing but sin phi into tan gamma x, okay, plus what is this term? This is B by O. I have divided everything by O. So, B by O is nothing but cos phi into tan gamma y. This must be equal to tan gamma O. This is the basic way in which we express relationships between the angles of one system and another. And please note, phi 1 is equal to, phi 1 is referred in the American system, is equal to 90 minus phi. So, this I think you agree and accept, so that we move on to the second problem. Okay. In the second problem, we want to express a relationship between lambda, gamma x, gamma y. You might say, what was the relation that we expressed in the previous one? In the previous one, we expressed a relation between orthogonal rake and back rake and side rake. Now, we want to express a relationship between inclination angle lambda and back rake and side rake. So, in that case, the whole trick lies in the definition of this particular triangle that you are going to consider. Just a moment. Whole trick is that you correctly assume the triangle here. This triangle means that you are establishing a relationship between three vertical distances. The vertical distance you travel down along the cutting edge in this case, okay, that means this way you are traveling down the rake surface on the cutting plane. If you do that, then what we have is that this segmental vertical distance under B and plus the segmental distance covered by S must be equal to the vertical segmental distance defined by this segment O. So, therefore, what we do is once again we remember the tangential relationship. It must be just one moment. What is this? Right. Here what we have is that we are going down the orthogonal what do you call it? We are going down the cutting plane by this distance. So, there is a vertical distance we have gone down. It should be equal to this distance that we go down plus this distance that we go up if this is vertical. So, in that case let us do one thing. We first go down in the along the orthogonal along the cutting plane and then we go further down along this then we go further down along this and ultimately we reach down along the back rake I mean in this direction by a certain amount. So, let us consider this particular relationship O tan lambda. O tan lambda gives us the distance we are going down along this direction. Okay. Assuming that lambda is positive, this is a downward movement. Now, assuming that the back rake angle is also positive, we will be going further down. So, we go down here and we go down here. so that these two distances are added up and they are together equal to the final distance that we move down in this direction. Okay. You might say that we are assuming some things here. What are they? We are assuming the sines of the angles that we are considering. To some extent, this is correct. Okay. So, if we have this particular assumption, we have a relation as shown here, O tan lambda plus S tan gamma x is equal to B tan gamma y. That is fine. So, once again let us divide everything by O, so that we have tan lambda plus sin phi 1. How does sin phi 1 come? If we divide everything by O, we have S by O here. S by O is equal to the sine of this angle. Now, what is this angle equal to? This is equal to the 90 degree minus phi. Let me use the pen and write it here. This is equal to phi. Therefore, this must be equal to phi 1. So, this is equal to phi once again. Okay. Now, I hope this figure is clear enough for you to understand. So, if this is phi, then what happens is, okay, this is phi. In that case, S by O will come out as cos phi. Okay. So, we write tan lambda plus cos phi into this distance once again is tan gamma x as found out here, equal to sin phi cos phi 1 sin phi. Why sin phi? Because B by O, B by O. So, that is equal to sin phi into tan gamma y. So, we have a relation between tan gamma y, tan lambda and gamma x and gamma y. Okay. Once we have established this, we understand that now we have a relationship between orthogonal rake and the two and back rake and side rake, and also inclination angle and back rake and side rake. Okay. So, let us take up the next problem. Okay. So, here we have another relation in which we are bringing in something else, that is a relationship between back rake and inclination angle and orthogonal rake. Previously, we were working with back rake and side rake and one of the angles in the orthogonal rake system. Now, two of the angles of the orthogonal rake system can be brought in and only one angle of the what do you call it, the American system can be considered. Let us see what sort of relation we have in that case. First of all, in this case, once again the whole thing lies in the consideration of the triangle. So, we will consider here that while we are going down in the while we are going down along the cutting edge, we go further down along the orthogonal direction, and the summation of these two distances will be equal to the distance that we cover on the back rake. Once again, here we are considering that lambda and gamma O, they are both positive. So, first of all, this the vertical distance covered by this segment must be L tan lambda. So, we write L tan lambda. The vertical distance covered by O must be O tan gamma O, this way, O tan gamma O, and the vertical distance covered along this direction, along the transverse direction, must be B tan gamma y, B tan gamma y. Okay. So, In this case, we establish a relationship as shown here, and if we divide it by b all through, we have L by b. So, let me use just a moment. Yes, if we use this expression, so we have divided by b, divided by b, divided by b, and this cancels out. So that finally, what we have is L by b. What is L by b? If this is phi, this must be phi, this must be phi, and therefore, we can say L by b is equal to sin phi, and therefore, we write L by b is sin phi into tan lambda plus the other one is O by b, that must be obviously cos phi into tan gamma O equal to tan gamma y. So, this way we understand that we can establish relationships between the angles by this sort of addition of vertical distances covered in different sections and then adding them up. Next, so first let me now we come on to something different. Up till now we have established relationships between orthogonal Rake angles. Now we will be establishing relationships between clearance angles, and since the inclination angle is shared between the rake surface and the principal flank, we can have a relation existing between the inclination angle and the two principal clearance angles in the American system. In main inclination angle and the two clearance angles existing in the American system for the principal flank. So, first of all, here what we do is, I have shown in dotted lines the distances that we are covering in two directions. What are these two distances? We are saying here that if we are moving down along this particular cutting edge, I am moving down the cutting edge by a certain distance, and therefore, I am undergoing some vertical distance which is given by L tan lambda. So, we have L tan lambda here, just a moment, L tan lambda. This is the vertical distance I cover on the cutting edge. After that, suppose I start moving down the flank now. In what way? I am moving down the flank in the transverse plane. So, this is the way I am moving down. If I move down the flank, then I am incurring some vertical distance. I am covering some vertical distance. How do you find out that vertical distance? We will be finding it out from this sort of a triangle, where this is nothing but S, and this angle as shown is alpha x. So, very therefore, we can definitely express a relationship where S, the vertical distance is of our interest. So, let us write it as V. So, we can immediately say that say cot alpha x must be equal to, what is it equal to? V by S, which means that the vertical distance is nothing but S cot alpha x, that is it, S cot alpha x. Once we establish this, we understand that once again the vertical distance relationship that we were dealing with, we can easily express the vertical distance this way, and that is what we have done. All right. And therefore, we have vertical distance down the cutting edge plus vertical distance down the transverse plane must be equal to the vertical distance down the this is side this is machine longitudinal plane must be equal to the vertical distance down in the transverse plane. And therefore, after dividing the whole equation by L, we have L cancelling out this by L and this by L. S by L, what is S by L? Once again we understand that this is nothing but phi, as this angle is phi, it is vertically opposite. So, S by L is nothing but cos phi, and therefore, we have this relationship tan lambda plus cos phi cot alpha must be equal to sin phi cot alpha y. Okay. So, this relation gives us a relation between lambda, alpha x and alpha y. Okay. So, we establish a relationship between clearance angles and the inclination angle. So, at this stage we understand that there is a relationship existing between rake angles, there is a relationship existing between the inclination angle and the clearance angles. So, there must be relationships existing between clearance angles in the American system and the clearance angle in the orthogonal system and the clearance angles in the what do you call it, in the normal rake system. Okay. So, one by one we are going to deal with them. So, let us see what we have in store in the next case. So, now we are going to, as discussed, we are going to have a relationship between the clearance angle in the orthogonal system. Okay. Clearance angle in the orthogonal system, clearance angle in the and the clearance angle in the back rake system, in the back clearance. So, relationship between back clearance and orthogonal clearance. Okay. So, in order to establish this relationship, what sort of relation we are going to get? We are going to take this triangle shown here. One side is going to lie in this section, another side is going to lie in the section pi o, and the other one is going to be obtained in the view of the cutting plane. Okay. But I think we have already crossed the time limit of the next lecture of this lecture. So, I leave this as an assignment to you. You can solve it yourselves and then we will compare notes. So, thank you very much.